Welcome to the virtual classroom of Chembase School of Chemistry. Sound clear? So today I'll be starting on the chemistry of alkanes, study pack 4C. I hope all of you got the study packs next to you. Right, as for study on the alkanes, alkanes are referred to as the saturated hydrocarbons, meaning it contains carbon-carbon single bonds throughout the carbon chain. And we discussed before the general formula of alkanes. It is CnH2n plus 2, which where the N is the number of carbon atoms. CnH2n plus 2. I think we wrote the general formula of alkanes before, and then I explained the general formula of cycloalkanes will be same as the general formula of alkenes. So cycloalkanes and alkenes have the same general formula. So this is N. N is number of carbon atoms. Number of carbon atoms is the N. So as for the homologous series of alkanes, a homologous series is a series of molecules which has the same general formula, the same functional group, and the adjacent molecules in the series will be differing by a CH2 group. The first few pages of this tute is very basic stuff which we have discussed before, and in fact the first few lessons of the O-level class, I'm just going to go a little bit faster in the first few pages. When it comes to the A-level lesson, I'm going to go a bit slow. So as for the chemical properties of the molecules which shows homology, molecules which follows the homologous series, is that all of the molecules in the homologous series follow the same chemical properties. They have the same chemical properties because they all have the same general formula. Yes, Kabishant, you have a question? So because they have the same general formula and because the same chemical properties are found, because of the functional groups are similar. And as for the homologous series, as you go down the homologous series, what happens is that the CH2 groups increase. So as the CH2 groups increases down the homologous series, their boiling and melting points increase. The reason for the increase in the boiling and melting points down the homologous series of alkane is due to the increase in number of electrons. As you go down the homologous series, as the number of electrons of alkanes increase, what happens is that the dispersion force strength increases. Dispersion force strength increase, right? So the increase in dispersion force strength results in increased intermolecular attraction. So that as the number of carbon atoms increase, the number of electrons in the molecule increases, which accounts for the increase in the strength of the intermolecular forces down the homologous series. As a result, the boiling and melting points increase. So not only boiling and melting points, as these are all simple covalent molecules, the intermolecular attractions also accounts for the change in the physical state. Now we know, for example, the solids will have the strongest intermolecular attraction, right? As for the liquids, they are quite weaker than the solids, and the gases will have the weakest intermolecular attraction. So therefore, in the homologous series from C1 to C4, they are classified as gases. C1 to C4, they are classified as gases. As for C5 to C15, they are liquids. And C16 and above, they are waxy solids. Waxy solids, right? Please copy this, because the physical state changes as the strength of the intermolecular attractions change down the homologous series. Is that clear? So the reason why the physical state changes as the number of carbon atoms increase is because the strength of the intermolecular attractions. In fact, there are different types of intermolecular attractions here. Of course, main attraction is dispersion dependent forces, which I'll be explaining under intermolecular forces later on, right? And also you can, for the time being, remember as a molecule becomes larger in size, they have more interactions. For example, the shorter molecules has less surface area, so there's less interactions between the molecule compared to long chain molecules. Long chain molecules have more interacting surface, so therefore they can form many or multiple intermolecular attractions between the molecules. So that's the reason as intermolecular attractions increase, their physical state changes from gases to liquid to waxy solids. So I mentioned the surface area is one of the main factors which determines the intermolecular attraction. So what happens when the molecule becomes branched? The long chain molecule becomes branched. What happens is that the surface area decreases with branching. Now see, this is a long chain molecule. Long chain molecules have greater intermolecular attractions because they're great interacting surface. So when the molecule becomes branched, then what happens? The surface area decreases, because as branching, the main carbon chain length decreases. So as a result, the interacting surface decreases with branching. So if I analyze the C5H12, I can draw 3 chain isomers, chain structural isomers. I think last lesson we discussed about the isomerism. You can draw 3 main chain isomers, which is one of it is pentane, which I'm drawing now, long chain hydrocarbon, and then I can make one branch to pentane and convert the pentane to 2-methyl propane. Remember, when you draw the structural isomers, always make sure you draw the displayed formula showing all the bonds. So this is 2-methyl propane, and then you get the 2,2-dimethyl propane with 2 branches, 2,2-dimethyl propane with 2 branches. So which one will have the highest boiling point? Yeah, which one will have the highest boiling point? 2,2-dimethyl propane or pentane? You can type the answer, please. This is 2, 2. That's right, methyl propane, and this is 2-methyl butane. So the highest one will be pentane, because that's the longest chain. Pentane has the longest chain, and then comes the 2-methyl butane, and the 2,2-dimethyl propane will be the smallest one, which has the lowest boiling point. So the boiling point decrease with increased branching. Is that clear? Please copy this. So as for the other physical properties of the alkenes other than the boiling and melting points, we can say alkenes, they are immiscible in water. Immiscible meaning they don't mix with water. Opposite of miscible is immiscible. So why they are immiscible with water? Because they don't form any intermolecular attractions with water molecules, because alkanes are mainly non-polar. Water is polar, alkanes are non-polar. So non-polar solute will not dissolve in a polar solvent. This also will be studying under Unit 2 in detail under solubility, concept of solubility, because a substance to be soluble, if it is a polar solute, the solvent also have to be polar. If the solute is non-polar, then the solvent should be non-polar in order to dissolve it. So polar solute will dissolve in polar solvents, non-polar solutes will dissolve in non-polar solvents. So these alkanes, whether it's branched or linear alkane, all of them are non-polar. So it will not dissolve in water, because water is a polar molecule. A polar molecule we'll be studying in Unit 2 later on. It's a molecule where the charge separation is found in the overall molecule. So alkanes are relatively unreactive. Relatively meaning relative to the alkenes. I'll be studying later on the next week, next session, about chemistry of alkenes. So alkanes are unreactive with respect to the alkenes. Alkenes are more reactive than alkanes. Because why they are unreactive? Because these carbon-carbon bonds which are found in alkanes, they are relatively inert. It's difficult to break these carbon-carbon bonds in alkane compared to the alkenes. That's the reason why alkanes are quite unreactive compared to the alkenes. In fact, these alkanes are very important in our lives. Alkanes are important as the hydrocarbon fuels, right? Petrol, diesel, kerosene. These are all fractions which is found in the crude oil. The crude oil is in fact a complex mixture of hydrocarbons. The crude oil itself is not very useful because crude oil is a complex mixture of hydrocarbons. It's a very viscous, thick, viscous, a greenish liquid. Itself has hardly any uses. In order to convert the crude oil into useful products, what we do is we carry out fractional distillation. Fractional distillation is a technique which is used to separate useful fractions based on their boiling points. We know we have done fractional distillation earlier. The mixture is heated and then when it vaporizes and get condensed at different levels based on their boiling melting points. So the lowest boiling point fraction will be at the top of the will distill first, followed by the higher boiling point fraction. So in the fractional distillation process of crude oil is done by this apparatus. This is known as a distillating tower or fractional distillation tower or the fractionating column. So what happens here, let me just enlarge this diagram for a bit, right? In this fractionating tower, what happens is that the crude oil is heated to a very high temperature around 450 to 500 degrees Celsius. Is heated using electric heaters and pumped in at the base of this fractionating tower. So what happens here is that the crude oil vaporizes up the column. As the crude oil vaporizes, it gets condensed at different levels based on their boiling points. So how it gets condensed is that each layer has trays. They are like horizontal trays here. Each tray contains thousands of bubble caps. Bubble cap is I just enlarge one bubble cap, right? So bubble caps, what does a bubble cap do is that bubble cap condenses each fraction at different points. Now what happens here, the crude oil is heated, so incoming heater goes right up, and when the vapors go and knock this roof of the bubble cap, they lose their kinetic energy. As the vapors knock the roof of the bubble cap, they lose their kinetic energy. As they lose their kinetic energy, they reform the intermolecular attractions and move on to the liquid state. And then you can extract that particular fraction. If there are any fractions which is lower boiling point than that fraction, that will vaporize to a higher level. So each tray there is condensation and revaporization taking place. Condensation and revaporization taking place. As a result, the fractions can be obtained based on their boiling point. So the lower boiling point fraction, which is obtained at the top, followed by the higher boiling point fractions, which obtained at the bottom. So the crude oil can be separated into useful fractions based on their boiling points, as explained. So the each tray contains various bubble caps, different numbers of bubble caps. So that's useful to separate the fractions based on their boiling points. I'll show you a small video how this is done industrially. Please let me know whether the video is clear with the voice. If it's not clear, let me know.
Crude oil is a thick, dark brown liquid found deep in the Earth's crust. It's a mixture of different hydrocarbons, molecules made of hydrogen and carbon. Some molecules in the mixture are very small, just a few atoms joined together. Others are far more complex, with many atoms forming long-chain molecules. But as a mixture, it's useless. The different hydrocarbons need separating. The technique used is distillation. This simple apparatus is set up in a fume cupboard. Mineral wool stops the mixture spitting when it's heated. Crude oil is dropped into the bottom of the tube. A collecting bottle is put in place. And a thermometer, level with the sidearm, monitors temperature. The final step is to gently heat the mixture by immersing the tube in a hot water bath. The hydrocarbons with lower boiling points begin to vaporise immediately. They're flammable, so it's safer not to heat with a naked flame. As the vapour rises, it enters the sidearm, where it cools and condenses. This happens at about 40 Celsius. The hydrocarbons which boil at this temperature drip down the sidearm and form our first fraction. It's a colourless liquid. The temperature stays at around 40 until all the hydrocarbons with this boiling point have vaporised. The hydrocarbons left behind aren't hot enough to vaporise. Their boiling points must be higher. Once the first fraction has been collected, it's safe to start heating with a Bunsen. As the temperature rises, other hydrocarbons begin to boil. A new fraction is collected at about 60 Celsius. It's slightly yellow in colour. And so the process continues. By carefully heating the oil and collecting the liquids which condense at a number of different temperatures, the many different hydrocarbons in crude oil can be separated. This is known as fractional distillation. On a larger scale, a fractionating column is used. The oil is heated with an electric heater for safety. The vapour is condensed by a Liebig condenser and is collected in a conical flask. Hot vapour rises up the fractionating column. It's a long way to go, and the further from the heat source, the cooler it gets. Most of the vapour condenses on the glass spiral inside the column and drips back into the mixture. Only the hydrocarbons, which are still vapours at the very top of the column, enter the sidearm and condense to liquid. Industry uses the same process, but on a mammoth scale, in huge fractional distillation columns. The hot oil enters near the bottom, at a temperature of 330 degrees Celsius. The column becomes cooler towards the top. Fractions which remain as vapour at 85 degrees Celsius go straight to the top and are piped away. Different hydrocarbons condense at different temperatures, running off at various levels. Those with lower boiling points are collected at the top oil into useful fractions, each containing molecules of a similar size.
So crude oil is a mixture of hydrocarbons which itself is not very useful. In order to convert the crude oil into useful products, it has to be fractionally distilled. Fractional distillation is based on boiling points of each fraction. In the refinery process, the crude oil is heated to a temperature about 350 to 400 degrees Celsius and pumped in at the base of the fractional distillation tower. The fractional distillation column contains a series of horizontal trays with bubble caps. As it boils, the vapor passes up the tower through a series of bubble caps and condenses as it rises further up the column at different temperatures. The smaller, lighter hydrocarbons with low boiling point distills off first at the top. The long chain heavy hydrocarbons with higher boiling point distills off at last. Now, the problem often encountered in this fractional distillation process is that the shorter chain fractions which is obtained by the fractional distillation, it's very small percentage compared to the long chain fractions. The shorter chain fraction which you obtain is much smaller percentage compared to the long chain fractions. And the shorter chain fractions, when you burn, you get less energy. Long chain fractions give out more energy. And also the light vehicles use shorter chain fractions like gasoline or petrol. The heavy vehicles, they use long chain fractions because long chain fractions produce more energy compared to the short chain fractions. So the amount of light vehicles are much more than the heavy vehicles. Therefore, the demand for the smaller, lighter fractions are much greater compared to the demand for the long chain fractions. So this demand cannot be met by the amount of hydrocarbons produced by the fractional distillation process. So therefore, what we do is we carry out the cracking process. Cracking is breaking down of a long chain hydrocarbon into a short chain hydrocarbon by breaking the carbon-carbon bond. So this cracking is achieved by silica, which is silicon dioxide, or alumina, which is aluminium oxide catalyst, when you heat to temperatures between 600 to 700 degrees Celsius. During cracking reaction, the long chain carbon-carbon bond is broken and short chain, more valuable molecules are produced. Usually, when you break a long chain alkane, you get a short chain alkane and a much shorter chain alkene. This molecule has 8 carbon atoms. When you crack this, if you get 6 carbon molecule at the one end, and on the other end you get a 2 carbon molecule, which is ethene. So you get an alkane and alkene during cracking. The alkane is shorter than the original alkane. The alkene molecule is much shorter, small chain, can be mostly ethene or butane. So you have octane here. When you crack, you get hexane and ethene. So during cracking process, you get a shorter chain alkene molecule, right, and an alkane molecule. When you add these two molecules, the carbons and the hydrogens of the alkane and alkene, you get the number of carbon atoms in the main main molecules. If you have molecule say C12H26 alkane, when you crack, if one of the molecule which is produced is C4H8 butene, you can easily predict the structure of the other molecule, which is C8H18, because when you add these two, 8 plus 4 is 12, right? 8 plus 4 is 12, 18 plus 8 will be 26. So when you add these two, you will get the main molecule. Is that clear? So cracking is the breaking of carbon-carbon bonds in the long chain hydrocarbon to obtain more useful smaller hydrocarbons. Short chain hydrocarbons like petrol has a demand greater than the supply due to the ever increasing numbers of motor vehicles. The demand exceeds that which can be obtained solely by fractional distillation. Also, a distillation tower produces more long chain fractions and less short chain hydrocarbons. Therefore, cracking larger molecules, more valuable smaller fractions can be obtained. That's the reason why the smaller fractions are more expensive compared to the longer fractions. So petrol is more costly compared to the diesel, right? Because there's less produced, cracking is involved, and plus there's more demand. So anything more demand will be more costly. So cracking takes place in a huge reactor where particles of powdered silica alumina are mixed with larger hydrocarbons at a temperature of 600 to 700 degrees Celsius. The cracked vapors containing smaller molecules are separated by distillation. Now you have the smaller molecules like alkenes, like ethene, propene, butene. That is not just wasted, rather it is used to make plastics. Ethene can be used to make the polymer polyethylene. We'll be discussing at the end of organic chemistry how to make polymers. Propene, polypropene, and likewise butene, polybutene. Next is the reformation reaction. Now, reformation of crude oil is basically the modification of the structure by converting a long chain structure into a cyclic structure with a ring. Or a cyclic structure, we may further condense it by making a ring in the middle. We'll be starting about these ring structures in A2, right? This is benzene ring, for example. So long chain ones, when you convert into a cyclic ones, it is known as reformation. So why do we need this type of reformation? Usually fuel, they undergo reformation. When you reform the fuel, you get more high quality fuel. The reason, when the long chain molecule is converted into a cyclic one, the amount of molecules which can be packed in a unit volume will be more. For example, I can pack more cyclic molecules in this volume than packing long chain molecules. If I have the same volume and you have long chain molecules, right, I can only pack few molecules right here. You can see the diagram. Only few molecules can be packed. But if it is like cyclic molecules, I can pack more. So by reformation, what we do is we convert a long chain one into cyclic one. So when we do that, there will be more fuel molecules to be packed in a given volume. That will enhance the property of the fuel. That means when you burn such fuel, it produces more heat energy per gram than unreformed fuel. That's why we have in the market, you have the octane 92 and 95, right? So octane 95 is more reformed than octane 92. Octane 95, if you pump to your vehicle, you can run more mileage compared to octane 92. And plus there are other properties of reformation, like it become more pure fuel, more pure. That means you'll have less engine issues when you use 95. You get more mileage, less engine issues compared to 92. 92 get less mileage and you get more impurities in 92, therefore you will have more engine issues later on. That's why they say generally if you have a new vehicle, don't use 92, use 95 octane. Of course it's a bit costly than the 92, but the costly because anyway you get a higher mileage than 92, so it's because of its reformed. So reformation is a modification of the structure by converting straight chain hydrocarbon into cyclic hydrocarbons. That means straight chain aliphatic, or it can be alicyclic one, into a branch chain or closed chain hydrocarbons or arenes. Arenes are the cyclic ones with a ring in the middle. Reforming is generally done on the naphtha fraction, which is fraction below gasoline. You can see in the fractional distillation tower, naphtha is below gasoline. Of course, you have to know the order of these fractions. You are not supposed to know the boiling points. Only thing we should know is as you go down, the boiling point increases. That's all. Because the long chain molecules are found, the heavy molecules are found at the bottom. The long chain heavy molecules have a higher boiling point compared to the short chain smaller molecules. Right, so you can see the naphtha fraction can be reformed to form more useful hydrocarbon molecules. Right. This is a process designed to increase the volume of gasoline that can be produced from a barrel of crude oil. When the molecule is branched or cyclic, there can be more molecules closely arranged in a given volume, thus increasing the efficiency of the fuel by giving out more energy upon combustion. Hydrocarbons in naphtha stream have roughly the same number of carbon atoms and those in gasoline. Naphtha and gasoline is very small difference in the number of carbon atoms, but the structure is generally more complex. Reforming rearranges hydrocarbons into gasoline. So gasoline, the hydrocarbon gasoline fraction and the naphtha fraction, if you count the number of carbon atoms, is almost the same. So only difference is the naphtha fraction is more complex fraction. You have more complex molecule than the gasoline fraction, even though both contain same number of carbon atoms. So in the reformation process, what we do is we simplify that complex structure of the naphtha into a more simpler one. Clear? So to do reformation, we need these conditions: platinum, rhodium, catalyst, temperature of 500 degrees Celsius. It is done under high pressure. Clear? Any questions up to this point? Right, let's see the environmental problems which is created by the burning of the hydrocarbon fuels. In fact, about 90% of the air pollution is due to the burning of the hydrocarbons. One of the main pollutants being the oxides of the oxygen, oxides of the carbon, carbon dioxide and carbon monoxide. In fact, carbon dioxide is not a toxic gas for humans, but it's harmful gas for the environment. because it's a greenhouse gas. As for carbon monoxide, which is produced as a result of incomplete combustion of the hydrocarbons, it is toxic for humans. The reason is this carbon monoxide combines with the hemoglobin in the blood. It combines with the hemoglobin in the blood to form the bright red compound, which is known as carboxyhemoglobin. So once hemoglobin turns to carboxyhemoglobin, the hemoglobin will be unable to carry oxygen to the organs, because hemoglobin has very high affinity towards the carbon monoxide than oxygen. So when you have carbon monoxide along with the oxygen, what happens? It prefers the carbon monoxide over oxygen. So that results in carboxyhemoglobin. So once hemoglobin turns to carboxyhemoglobin, what happens? That particular hemoglobin will not be able to carry oxygen anymore. So this results in headaches, because our brain is very sensitive to oxygen. That's one of the most sensitive organs. And prolonged exposure to carbon monoxide will result in death. Right? So it's very important to know that carbon monoxide has no color, no smell. So you will not know you are inhaling carbon monoxide till you faint, right? Because it's a very big issue. Like, for example, people have died inhaling carbon monoxide that is produced during incomplete combustion. Especially, people putting the barbecues indoor have died, right? Because barbecue is not to be put indoors, it has to be outdoors. Because indoors, when you put barbecue, what happens is that there will be more circulation of carbon monoxide than carbon dioxide, because there's less oxygen inside. When there's less oxygen, the fuel burns incompletely, resulting in complete combustion. So as for carbon dioxide, it's not a toxic gas. And it's not a big issue because the carbon cycle regulates the amount of carbon dioxide. The carbon cycle takes care of it. So only issue with the carbon dioxide is that it causes global warming, right? It's a greenhouse gas. So the IR radiation emitted from the Earth to the atmosphere is reabsorbed by the carbon dioxide and emits back to the Earth. So as a result, the Earth is kept warm. That's in short the greenhouse effect. So when there's excessive of greenhouse gases like carbon dioxide, the global warming is issue. So this global warming results in sudden climate changes, and polar ice caps melt and the sea level rises. So all those issues are due to the carbon dioxide. As for the oxides of nitrogen, it causes permanent lung damage, severe irritation, and nitrogen dioxide can dissolve, or it dissolves with the rainwater to form acid rain. Oxides of sulfur likewise causes acid rain. It dissolves in water to form the sulfurous acid, H2SO3, not sulfuric, sulfurous first. Sulfur trioxide dissolves in water to give sulfuric, not sulfur dioxide. So once the sulfurous is formed, which is H2SO3, that can further react with oxygen and form sulfuric acid, right? So I'll write the reaction here, which is right. So that's sulfur dioxide, and there are so many other toxic gases like lead particles. Causes brain damage, irreversible brain damage, and unburned hydrocarbons are carcinogenic, cancer causing. Of course, now the lead, you get the unleaded fuel now, unleaded petrol. So that issue is not there anymore by burning hydrocarbons. So, right. So the best solution for this is use alternative sources, such as using motor vehicles running out of solar energy or fuel cells, like any other, like electric vehicles, for example. So alternatives are one of the best solutions for this problem. So, and minimize the use of the hydrocarbon fuels. So the use of hydrocarbon fuels increases day by day, so that increase adds to the level of pollutants released into the atmosphere. And also the demand for this petroleum fuel increases. So the petroleum is a finite resource, limited resource. So once you run out of all the petrol or all the crude oil, then you have to wait for long thousands of years for it to reform again. So because the sustainability of crude oil is also limited, and then the combustion produces harmful products, it's time to move on to. Now, of course, we have moved on to alternatives such as hybrid vehicles or electric vehicles. Even some countries have vehicles running out of fuel cells and solar power. Fuel cell in the sense like you pump hydrogen gas and oxygen gas. A chemical reaction takes place producing water, and as a result the electricity is produced. We'll be studying in detail about fuel cells later on. Okay, right, so that's the possible alternative sources. Next, let us see what is carbon neutral and the meaning of the term the carbon footprint. The carbon footprint basically gives you idea about the total amount of the greenhouse gases produced during combustion reaction. So the carbon footprint is a way or a method to measure the total amount of carbon dioxide produced from its production to its combustion. Not only when the fuel is burnt, not only at that point, even at the point of the production or extraction of the fuel, the amount of carbon dioxide released is measured by the carbon footprint. So the carbon footprint, if you take up a fossil fuel, it is the amount of carbon which is released by combustion process, and as a result of the transportation there's a carbon dioxide release, because you have to extract the crude oil and transport to the extracting site, so that during transportation, before even burning the fuel, you have burned and released carbon dioxide because of the transportation issue, and refining and then distribution, all those all those produces the carbon dioxide gas, right? So in order to calculate the carbon footprint of a biofuel, that is the amount of carbon dioxide absorbed during the growth, biofuel meaning like, for example, bioethanol, right? So if you want to calculate the carbon footprint of such fuel, then you have to first of all calculate how much of carbon dioxide that particular plant has absorbed, and then you deduct or subtract the carbon dioxide which is released during the combustion, right? So when you compare the carbon dioxide release overall during combustion, it will be much less compared to the fossil fuels, because fossil fuels because these biofuels, they already absorb certain amount of carbon dioxide from the atmosphere for this manufacturing of the fuel, and when it releases I mean, the overall, when you analyze, the amount which releases is less than the amount which is compared to the hydrocarbon fuels. Is that clear? And there's no fuel with a zero carbon footprint. There's no fuel with a zero carbon footprint. Any fuel will have a footprint. So carbon neutrality is a concept when the amount of carbon absorbed by a fuel, if it is same as the amount of carbon which is released during the combustion, such is referred to as a carbon neutral fuel, right? The amount of carbon which is absorbed during its manufacture, if it is equal to the amount of carbon dioxide released upon its combustion, such is referred to as a carbon neutral fuel. In fact, in reality, there is nothing called a carbon neutral fuel. There's nothing called a carbon neutral fuel in reality, because even if you, for the argument's sake, say take a plant or take a tree, let's assume it absorbs X amount of carbon dioxide through its lifespan of 100 years, for example, and for the argument's sake, if you say it releases X amount of carbon dioxide during the combustion of the wood, the tree, still it is not mentioned as carbon neutral, because it's not just burning the fuel, there are so many things to consider. For example, chopping down the plant, the tree, a lot of carbon dioxide is released because people have to come to chop down the tree, so they don't come on horseback, they have to come on a vehicle, so carbon dioxide release. And also the instruments which they use for chopping down the tree is, for example, axe or whatever saw. They're all from iron, made from iron. Iron doesn't come from the sky, we have to extract it, so there's a lot of energy release in that point. Now, even after taking the wood out, but to transport that to the site, so there is sort of carbon dioxide release. So argument goes on like that, so you cannot say any fuel is carbon neutral. Likewise, the electric vehicles, you can't say electric vehicle is carbon neutral, even though it doesn't release any carbon dioxide at the point of combustion. The manufacturing of the vehicle, you have already polluted the environment somewhere else out in the world. Maybe at the point of driving you are not polluting, that's true, but you already polluted somewhere else. So you cannot prove that any fuel is carbon neutral. Even electricity, even if your car is running out of electric current, that's the case. And even if you had a fuel cell, the fuel cell needs hydrogen and oxygen, right? It needs hydrogen and oxygen. So still, what happens is hydrogen, oxygen just not extracted. You have to extract it. It doesn't come just, right. So that extraction process releases carbon dioxide. So likewise, you cannot prove any fuel to be a carbon neutral fuel. So carbon neutral fuel means the amount of carbon which is absorbed, if it is same as the amount of carbon which is released, such is referred to as carbon neutral. Right? Is that clear? If you apply the concept of the carbon neutrality to certain fuels, some fuels you can be very close to carbon neutral. For example, the bioethanol, which is, they say it's carbon, actually it's not carbon neutral, but it is very close to carbon neutrality, right? That is, if you make bioethanol by the fermentation of the hydrocarbons, right? So now since recent, the bioethanol is very widely used in as a fuel in Brazil, because Brazil has a very good environment to grow sugarcane, right? So what happens is that they manufacture ethanol out of sugarcane, and then that's why a fermentation process, and then you add the ethanol to gasoline. Ethanol to gasoline. Gasoline is petrol. So when you add ethanol to gasoline, you get a new fuel which is known as the gasol, right? You get the gasol. So gasol is gasoline plus ethanol. If you go to Brazil, you will see, I have seen the pictures in the fuel station. You have the gasoline and at one end and gasol on the other end. So gasol meaning just it is not ethanol alone. Gasoline is mixed with ethanol, so therefore you cannot say it has no environmental pollution. It do causes environmental pollution like any other hydrocarbon, but the manufacturing process, it is renewable because we use ethanol. Ethanol is renewable as it is obtained by the burning of the fossil, obtained by the fermentation of the sugar cane, right? There's a discussion on that, and the reactions of alkanes. Alkanes, we mainly study two types of reactions. One is the combustion, and the other type is substitution. The combustion is burning of hydrocarbon. In fact, there are two types of combustion. The product of combustion depends on the supply of oxygen. The products of combustion depends on the supply of oxygen. If you have, say, a limited supply of oxygen, then the combustion products will be carbon monoxide and water, or even sometimes you can even get carbon plus water if the supply of oxygen is much limited. But if you have plentiful supply of oxygen, then the products will be carbon dioxide plus water. So the products of the combustion reaction depends on the supply of the oxygen. So whenever you burn hydrocarbons completely, which is complete combustion, it releases more energy compared to the incomplete combustion. When you burn hydrocarbons completely, energy release will be much more than the incomplete combustion. So combustion is burning, that is reaction with oxygen. Two types of combustion. The incomplete combustion, remember, it's not only carbon monoxide, even carbon soot, just carbon solid, can also be produced. So the complete combustion gives out more energy with respect to the incomplete combustion. And also the hydrocarbons, which has more carbon atoms, meaning long chain hydrocarbons, it has more carbon atoms, it releases more energy compared to the short chain hydrocarbons, which has less carbon atoms. Right? That's why the heavy vehicles, they use long chain ones. Light vehicles, they use short chain hydrocarbons. Let us try to write a common balanced general equation to represent the combustion of alkane. So this is alkane, common general equation. Oxygen gives carbon dioxide plus water. Can you please balance this equation in terms of N? I'll just give you a minute to balance this equation in terms of N. Yeah, start. So there's N amount of carbon, so I put N in front of carbon dioxide in order to balance the carbon. As for hydrogen, there's 2N plus 2 hydrogen here, so I'm going to put N plus 1. N plus 1 times 2 is 2N plus 2. So carbon is balanced, hydrogen is balanced, the left is the oxygen. If you analyze on this side, on the right side, there's 2N oxygen, and here there's N plus 1 oxygen. There's 2N here, and there is N plus 1 over there. So 2N and N plus 1 together will be 3N plus 1 oxygen. So to balance the 3N plus 1 oxygen, it's 3N plus 1 over 2. Why is that? Because 3N plus 1 divided by 2 multiplied by 2 is simply 3N plus 1. So you have 3N plus 1 oxygen on the reactant side as well as on the product side. Is that clear? The next reaction is the halogenation of the alkane. It's a substitution reaction. Halogenation is simply introduction of a halogen atom to alkane. That is substitution. That means you remove one of the hydrogens or many of the hydrogens and substitute a halogen in the place of the hydrogen. So a substitution or reaction occurs in the presence of diffuse sunlight. Diffuse sunlight meaning indirect sunlight, because direct sunlight you cannot use as it is explosive. So we use indirect sunlight, which is diffuse sunlight, or you can even simply use UV light. In that case, you can convert alkane to a haloalkane. Haloalkane is halogenoalkane. So the fluorine, chlorine, bromine, of course not iodine, because iodine, the iodine bond is very strong. So I mean, the intermolecular attractions are strong. So the normal light is not sufficient, or the UV light is not sufficient to break the iodine bond. So, but fluorine, chlorine, bromine will interact with the alkanes in the presence of diffuse sunlight to form haloalkanes. Direct sunlight is explosive, so that's why we don't use direct sunlight. So the sunlight, it acts as a photocatalyst. In fact, it is helpful to initiate the chemical reaction, that is by giving insufficient activation energy. Is that clear? I'm not going to read the note because just to save time. So let us see how tetrachloromethane is produced by methane stepwise. Now, see, this is methane. In the first step, when you add chlorine in the presence of UV light, you get monosubstituted chloromethane. Along with that, HCl is produced. So all this substitution produces a byproduct. And this, if you further react with chlorine in the presence of UV light, you get dichloromethane, right? So step by step. For the chlorine, UV light, tetrachloromethane. Sorry, this is trichloromethane. This is monochloromethane first, dichloromethane, trichloromethane. Each time you get HCl as a byproduct. Step by step, you substitute all the 4 hydrogens at last till you get tetrachloromethane. So this is how tetrachloromethane is produced by methane stepwise. Please copy this. Right, the mechanisms of alkane. We just only got one mechanism, which is the substitution mechanism. In reaction mechanism basically tells you all the details about the reaction, details in the sense like how the bonds are broken. We discussed earlier the homolytic fission, heterolytic fissions. I'll explain later on that again, and how the bonds are made, the order of breaking and making bonds. All this information about the reaction can be obtained by studying reaction mechanisms. Now, always a weaker bond is broken first, and the stronger bond is broken last, and that is a bond breaking process. When the bonds are made, always the stronger bond is made first, and the weaker bond is made last. So the bond breaking process, the weak bond breaks first, and when making process, the strong bond is made first. So the order of making and breaking bonds and how the bonds are broken, how the bonds are formed, is explained by the reaction mechanism. So the bond breaking are of 2 types: homolytic bond fission as well as heterolytic bond fission. Heterolytic meaning the bond is broken so that one atom receives both the electrons. For example, if I have, say, hydrochloric HCl, it's covalent bond. We know chlorine is more electronegative than hydrogen because it's plus 17 charge. Electronegativity is the ability of atom to pull the bonding pair of electrons itself. So as a result, the carbon halogen bond breaks towards the chlorine. When the bond completely breaks towards one atom, that will result in cation and anion. Right? This is known as heterolytic bond fission. That happens in polar molecules. Likewise, the CCl bond. It's a polar bond. So bond will be broken so that one atom receives none, whereas the other atom receives both the electrons. So heterolytic bond fission, bond is broken so that the more electronegative element attracts the bonding pair of electrons, and the less electronegative one receives none. Right? Is that clear? So this is heterolytic fission. So when a bond is broken, always there's a rule when you move arrows in a reaction mechanism. Always, if a bond is broken, the arrow should start from the middle of the bond and should point to the atom where the bond is broken. That's the rule. Right? And if both electrons are moved, we use fully headed arrows, and only one electron is moved, we use half headed arrows. I'll explain that in the next question. So the reaction mechanisms provide information on the bonds which are broken during the reaction, bonds which are formed during the reaction, how bonds are broken, and the order of breaking and making bonds. Heterolytic reaction mechanism, a curved arrow is used to indicate the movement of a pair of electrons. If an electron pair is moved, then the arrow should start at a lone pair, or if the bond is broken, then the arrow should start at the middle of the bond. Likewise, if a bond is formed, the point of the arrow should end between the bonded atoms. If the bond is broken, the arrow should end at the atom in which the lone pair is donated. That means arrow should end at the atom where the lone pair is given, donated. And the bond is broken, it should start from the middle of the bond, should point to the atom where the bond is broken. You can copy these two. Homolytic bond fission, that happens in non-polar molecules generally. Homolytic bond fission is a bond breaking so that each atom receives one electron. So when a bond is broken homolytically, the movement of arrows should be such that it should start from the middle of the bond and it should point to the atom in which the bond is broken. So you use fishhook arrows. It's called the fishhook arrow. Fishhook arrow is used to show movement of a single electron. A double-headed arrow is used to show a movement of a pair of electrons. So this will result in atoms, because each atom takes its own electron from the covalent bond. So that will basically give rise to free radicals. Free radicals are nothing but neutral atoms. These are referred to as free radicals. They are neutral atoms. The neutral atoms produced by the homolytic bond fission are referred to as free radicals. I think we discussed this before under the basic explanation of the organic chemistry, right? So a half-pointed curved arrow like a fishhook is used to represent the movement of a single electron. The arrow should start at the middle of the bond, should point towards the atom. Please copy this. Let's see the mechanism of the alkane with reaction with the halogens. This is known as a free radical substitution mechanism. You know what is substitution now, and you will know shortly why we call this free radical substitution. There are three steps of the mechanism. The first step is known as the initiation step. The first step is known as the initiation step, right, where the UV radiation is utilized to break the chlorine-chlorine bond homolytically. That's known as initiation step, right? So I'm going to write the step here. The chlorine-chlorine bond was a non-polar molecule. Bond breaks homolytically. That happens in presence of UV light or diffuse sunlight. That results in free radicals. This is the initiation step. Always remember, a free radical will always react with a free radical. A free radical will only react with a free radical to form a neutral molecule. So in the propagation step, I'm going to show the carbon-hydrogen bond here. It's just methane, but I highlighted the carbon-hydrogen bond because I'm going to substitute this particular hydrogen with this chlorine. So I just shown the one carbon-hydrogen bond, right? So now this bond is a polar bond. Even the whole molecule is non-polar, CH bond is a polar bond. But this bond breaks not heterolytically, even though it's polar, it breaks homolytically because of this free radical, right? Because the free radical forces the bond fission as homolytic. The reason being, always free radical reacts only with a free radical. A free radical reacts only with a free radical. So free radical takes a free radical. So how it takes a free radical? As a result of the homolytic bond fission. So this bond breaks homolytically like this. So now this bond breaks homolytically. This chlorine takes the hydrogen and it will produce methyl free radical. An organic free radical inorganic free radical combines with organic free radical to form an inorganic product, and the resultant will be an organic free radical. So free radical always needs a free radical to react. So free radical reacts with a free radical to form HCl. That will result in the free radical form. So this methyl free radical will react with another chlorine molecule, because initially we have got one chlorine here, out of which they produces two chlorine free radicals, out of which one reacts with the methane molecule. The remaining free radical is just there in the system. That will take part in the termination step. And now you produces a methyl free radical in the first step of propagation. That free radical needs what? A radical needs whom to react? Yes, I'd like to hear from you the answers. I will, just type the answer. If you want me to enable the microphone, let me know. another free radical, right? So how to produce a free radical from this chlorine as a result of the homolytic bond fission, right? So it forces it to break homolytically. Don't much worry about the movement of the arrows. So you get a chlorine free radical and CH3Cl, right? So now you have the main product produced as a result of the free radical substitution reaction of methane with chlorine. You have chloromethane produced along with HCl. These are the two products of the propagation step. And for the termination step, any two free radicals can react and terminate the reaction. Now can you see, I said there are two chlorine free radicals produced initially, out of which one reacts in the propagation step. There's one chlorine free radical remains, and the remaining free radical and the chlorine free radical produced in the propagation step, those two will react. The chlorine which is produced in the propagation step and the chlorine which is produced in the initiation step will react to form chlorine gas. That is the termination. Termination is simply reaction between two free radicals. That terminates, ends the reaction. You can also notice there's methyl free radical produced here. That methyl free radical may also combine with this chlorine free radical. Any two free radicals can react. So you have methyl free radical reacting with chlorine free radical to form chloromethane. Or even two methyl free radicals can combine. So there's enough of methyl free radicals in the system, like two chlorine free radicals combined before. Even two methyl free radicals can combine to form C2H6, ethane CH3CH3. So you can notice now there are three possible termination steps for just one single substitution of a hydrogen. So one single substitution of hydrogen has two propagation steps and three termination steps, right? So initiation is free radicals are generated by homolytic fission by the energy given by UV light. Propagation, the highly reactive radical produced in the initiation step abstracts the hydrogen from the methane, forming HCl and methyl radical. The reaction continues as the methyl radical reacts with chlorine to form chlorine radical. This repeats over and over. The radicals combine to form a molecule. This brings end to the reaction. Right? Any questions? Never use fully headed arrows in the mechanism. You have to use the half headed arrows because it's all homolytic bond fission. And the last question, I'm going to explain to you how tetrachloromethane, I mentioned before how CCl4 is produced here. Let us see the mechanism of this production of CCl4. Right? Now I explained how when one of the hydrogen is substituted, what happens? When one hydrogen is substituted, to substitute one hydrogen, you need to have two propagation steps and three termination steps for just one hydrogen, right? If it is for one hydrogen, there are two propagation steps and three termination steps. If I substitute two hydrogens, how many propagation steps will be there? If there are two hydrogens, for one, if there are two propagation steps, for two hydrogens, how many propagation steps will be there? Yeah? Two will have four. If I'm to substitute three hydrogens, right? Three hydrogens, how many propagation steps? 6, that's right. If I'm to substitute all four hydrogens, how many? 8. Great. So I'm going to draw the 8 propagation steps. And look, it's very simple. If you understand the first two steps, you have to just repeat the first two steps 3 more times, that's all. The basic principle is this. a chlorine free radical reacts with an organic free radical. An organic free radical reacts with a chlorine free radical. Inorganic to organic, organic to inorganic. You repeat this pattern 3 more times. So initiation step is the same. Chlorine free radicals. Chlorine breaks homolytically, resulting chlorine free radicals. And in the propagation, we'll write the first two which we wrote before. We'll just show the HCl HC bond. What happens? Homolytic fission here, resulting methyl free radical and HCl. And the methyl free radical reacts with chlorine free radical, breaks a bond homolytically, chloromethane and chlorine free radical. Now what to do? I'm going to show the carbon hydrogen, just the same chloromethane I have drawn here. Same chloromethane I have drawn here. Only difference is I have shown the CH bond. Just the CH bond. Why I showed that bond? Because I'm going to break this bond homolytically, right? That's why I shown that bond. So homolytic fission, that will give rise to CH2, Cl and HCl. And then this is the organic free radical attacking the inorganic molecule chlorine. The first two steps you repeat. CH2Cl free radical attacking this. So that will give you chlorine free radical and CH2Cl2. This is 2 chlorine substituted. So the first two steps you notice, you get a chlorine free radical and haloalkane, and that chlorine free radical attacks the haloalkane again. So same thing happens here. This chlorine free radical attacks this haloalkane again. So you have Cl2, CH, and then chlorine free radical. I'm showing the CH again. And then what happens? You get CHCl2 free radical and HCl and HCl. And then the chlorine reacts with CH2Cl2 Cl2 free radical, homolytic fission, CHCl3 and chlorine free radical. Now can you notice 3 hydrogen substituted? There are 1, 2, 3, 4, 5, 6 steps. The last hydrogen substitute, there's 2 steps to go. So I'm going to show this CH, homolytic fission, resulting CCl3 free radical and HCl, and that reacts with chlorine. The final CCl4 is produced. So if you understand the first 2 steps, you just look at the first 2 steps. You only need to know the first 2 steps, and by looking at the first 2 steps you can predict the rest of the steps. Is that clear? So the 8 steps are mentioned here. You need to practice these 8 steps, right? Any questions? Do please copy this and please practice. Of course, now don't write the termination steps now. Termination, if the one substitution has 3 termination, all 4 substitutions will have how many terminations then? Yeah? If one has 3, all 4 hydrogens substitute 12 termination steps. So when you're free, just enjoy the 12 termination steps. You write the 12 termination steps. Don't write it now. Okay. Copy this, please. There's a question here. Should be CH2 Cl2 in the third to last. Let me check. Adam, can you just show me which one you're referring to? I will enable your writing control. Just click on this icon here on the screen. Select the icon and show me which one you're meaning. Select the icon, click on the icon. I have given you writing control on the board. Yeah, Adam, please do it. Click on the pencil icon and then you get the icon on the screen, the cursor on the screen. That's right. Okay, thanks for that. Let me check. Yeah, maybe it's a mistake. I had to correct it. CH2 Cl2, that takes a free radical. This is a CHCl2. That's right. This is just the H2 is missing here, right? That's right. There's extra hydrogen. I should erase that. That's a mistake. I don't know how many of you, noticed that. Only he has noticed it, right? I have put extra hydrogen there, so that has to be corrected. Thanks for that reminder, correction, right? So that should be only CH because it comes from this CH here, so it should be the same thing. CH2, so it takes a chlorine free radical. So a free radical reacts with free radical. Organic free radical combines with the inorganic free radical. You should be able to write these steps. You might not get to write all the steps at the exam, but at least you should be able to write halfway through, right? So please do practice that. And with that note, I have completed the entire lesson. So see you next time, the usual class. With that, I conclude for today.